Hello, my name is Justin Henderson. I'm currently working under Dr. Park in the Mechanical Engineering Department and in the field of robotics. The overall research goal is to develop a four-wheeled leg robotic system to ultimately create a more robust method of locomotion for both indoor and outdoor travel. But to get to that level of development, scouting and testing of individual parts of the robot, in this case hip and leg actuators, is required to fully understand the implications of full-body robot dynamics. The testing of choice is done via a rotary inverted pendulum due to its robustness in controls and limitless motor position. Two different control modes can be executed, swing-up controller and a balance controller. These can work in tandem, but they also work alone. In this case, I develop a balance controller. For hardware, a few components are required. We have a servo that spins around the z-axis, an arm to hold the pendulum, an encoder that sits on the end of that arm that will measure the pendulum position, and a pendulum that will hang off of that encoder, and a microcontroller that will control the motor. The catch about this servo is that it uses CAN communication to receive commands, meaning that matching controllers must be able to handle CAN communication as well as serial communication from the encoder and the computer. The STM446RE is an ideal choice for its ability to run several threads in the same code. These are the related balancing simulation results from using two PID controllers, one for the servo and one for the pendulum. I set up a small motor movement so that the simulation can respond accordingly. That's the 0.1 here. The motor overshoots by about 12% with a settling time around 10 seconds. The rod only shifts about 0.08 radians, or about 4.5 degrees, before balancing back to the vertical position. The force does saturate the motor at negative 12 newtons for a split second, so no permanent damage immediately, although executing this program consistently may cause some damage over time. For controller results, the code is split up into a couple different control modes. Initialization moves the motor back to the zero position in a gentle way so the motor doesn't burn out. Motor jog mode tests that the motor is able to receive commands from the computer, meaning that both serial and CAN communication are working. Encoder jog mode links the encoder position to the motor position, signifying that the motor can be controlled using inputs from the encoder. In progress, we have quite a few things, but the most important are integration of the control methods to the microcontroller, and developing more control methods. If we happen to run across a method that controls the motor more efficiently than others, it may help the leg and full body dynamics operate more efficiently. In conclusion, the STM microcontroller has proven to be capable of running CAN and serial communication simultaneously, and it's known to handle at least one motor at a time. Looking forward, it may be crucial to test how many motors this controller can handle, since it may cut down quite a bit of wiring and processing power needed. Finally, the next big step is to develop a wheeled leg test stand to explore motor stress as well as multi-motor dynamics. Thank you.